warm air heating system. A warm air heating system is convective, which means that we basically have air heating air. Hydronic baseboards are also a convection type of system where the cool air enters the bottom of the baseboard, and as it warms, it creates an airflow up through the baseboard and heats the room from air to air, basically. Conductive is anything that's touching a warm surface. Think of a metal pot on a stove. As the burner heats up, the pot gets hot, and if you've got a metal handle, you're going to get burnt when you pick it up. So that's conductive heat, which means anything that's touching the floor surface in a radiant system will warm up. So all of your furniture, anything that you've got sits on the floor will be warm to the touch. And then radiant heat transfer is the radiant heat coming from the sun is a good example. Even though there's 93 million miles between us and the sun, we can still feel heat from the sun. That's what makes our planet warm. At 14 BTUs per square foot, radiant floor will start a convection current. Warm air rises, so as it warms the air next to the floor, that warm air will start to rise, and we'll pick up convection with radiant floor. Conductive we pick up with radiant floor because anything touching the floor warms up, and of course radiant is the transfer of heat energy from one source to another. Radiant heat also is 360-degree heat, which means that if we have a tube in the floor, that tube will heat up and down, so we need to make some provision to direct the heat where we need it. Some of the advantages to radiant heat, the big one is air circulation and cleanliness. If you've got a forced air system, if you see on the lower left corner, we've got air temperatures all over the place, and we've got air swirling around as the furnace comes on and starts to blow heat everywhere. And then you also have registers and grills that have to be open and available for the heat to come through. And then the last part would be things like furnace filters and air cleaners. By radiant heat, we're not moving as much air. We're not heating with that air. So it keeps the dust and the mold down because we're not creating that huge air current, which also helps allergies and other ailments like emphysema or any kind of breathing or problems like that. Energy savings. Because we can direct the heat to where we need it, and radiant heat has such a large thermal mass, we're using the whole floor as a radiator, it helps us cut down on the energy cost. And of course, the better built the structure, the better energy efficiency we'll get from that. So radiant heat is typically around 25% more efficient just by installing radiant heat over forced air. Comfort. Hot goes to cold always. And a good example of that is if you go into a grocery store and you go to the frozen food aisle where the freezers are, as you walk by those freezers, it feels cold. That's not actually the cold traveling out of the freezer. It's the cold pulling the heat away from your body. Humans are 98.6 degrees, and anytime that temperature is below that 98.6, we're losing heat to our surroundings. So that the more even we can keep the heat around our body, the more comfortable we'll be and the more efficient the heating system is. Zoning ability. The great thing about radiant floor heat is we put the loops in the floor, and we can actually zone each individual loop. We can zone every room in the house to have its own thermostat. We can zone by groups, which means you may put the bedrooms all on one zone because Most people like it cooler in the bedroom at night. Your kitchen and your dining room would be on a zone because those are living areas, and typically we like those a little warmer. You could do zoning bathrooms and kitchens that have tile floors. You want that tile floor to be nice and warm, so we could zone those in one zone. So the zonability is a big plus to radiant floor heating. This is an example of zoning. There are actually 9 zone pumps in this installation, and each one of those pumps takes care of a different part of the house. Gives us a lot of flexibility into how we can heat the house. Next, we'll cover some system components: the pipe, the manifolds, heat transfer plates, floor panel systems, preassembled panels. We want to be able to discuss some of the types of equipment that goes into the system. The pipe that we've been using for the last 30 years is typically PEX pipe, and there are really 3 different kinds of PEX. PEX A is an angle method PEX, named for the man who discovered cross-linking. The term PEX is polyethylene cross-link pipe. And what we mean by cross-linking is, if you think of a fence on a farm, you've got a barbed wire fence where each individual strand runs from post to post to post, and you might have 4 or 5 strands all running horizontal to each other and not really touching. That's what we would have in a typical piece of polyethylene pipe. When we cross-link the pipe, what we do is we take those horizontal strands and we link them side to side. If you might think of like a chain link fence. Chain link fence is so much stronger than a strand fence. The same thing happens with the pipe. When we cross-link it, we bind the molecules not only end to end but from side to side, and we make that pipe much stronger by binding all those molecules together side to side and top to bottom, you might say. The angle method is a peroxide method. Peroxide is added as the tubing is being extruded, and because of that extra process as the tubing is being extruded, they can't run it as fast, which means that the machines can't produce as much pipe in a day as some of the other methods. We typically call that PEX A. PEX B is a silane method pipe. It's a moisture cure method, which means that the pipe is actually cross-linked after it's extruded. It's heated up, and the heat and moisture by adding the chemicals to it causes the pipe to cross-link at silonal condensation between the molecules. PEX C is a less common pipe. We typically see this in pipe diameters above 2 inch. It's an easier process to accomplish. It's an electron beam process where you shoot particles into the pipe and cause it to cross-link through the electrons and the carbon-hydrogen bonds. The PEX C pipe is usually a bit stiffer than the other types of pipe, and again, it's typically used in pipe above 2 inch just because of the difficulty to cross-link with the other methods once you get to that size. The last one is what we call PEX Al PEX. It's a PEX pipe with an aluminum layer sandwiched between 2 layers of PEX. And that metal layer serves as the oxygen barrier for the pipe. It also serves as a structural component to the pipe and makes it much more rigid, which means you can form PEX aluminum pipe. When you bend it, it will stay in whatever form you bend it to. Typical PEX pipe is the extruded pipe, and then we always, for radiant floor, we always add what's called an EVOH layer. And that EVOH stands for ethylene vinyl alcohol. And what that does, it keeps the oxygen from migrating through the pipe. Plastic pipe or plastic of any kind will let oxygen travel through the pipe. Oxygen is bad in radiant systems. It causes corrosion. Also could cause an airlock in the pipe, and that's a bad thing also. A common example of an EVOH barrier would be a bag of potato chips. When you try to open a bag of potato chips, you have to pull really hard to get it open, and that EVOH layer inside the bag keeps the oxygen out of the chips and keeps them from going stale. So we're trying to keep our water in our pipe from going stale and causing corrosion and airlocks. PEX pipe is basically just PEX and the O2 barrier. These are just an example of the typical sizes we would use in radiant floor, 3/8 through 1 inch. The ones we use most often are going to be 1/2 inch and 5/8. We use those because of the loop lengths that we can use for those, and the bend radiuses, and the ability to carry heat. PEX pipe has a maximum temperature of 200 degrees at 80 psi. Most of the systems we work with are running at about 12 to 15 psi, so the pressure isn't a problem for us. The temperature could be depending on the application. So PEX pipe is rated at 200 degrees maximum. PEX aluminum pipe has that inner core of PEX, usually a welded aluminum layer. That aluminum layer is usually 1 to 2 millimeters thick, and then it has a PEX layer on the outside. One thing that PEX aluminum does is it protects your oxygen barrier. With the regular PEX pipe, if you're not careful, you can actually pull some of that oxygen barrier off. If you're pulling it through wood joist or something, sometimes you can skin a little bit of it off. With the PEX aluminum, that oxygen barrier is protected with a layer of PEX on the outside. The PEX aluminum pipe is bendable. When you bend it, it stays. That's good and bad. If you're installing it, sometimes it can be difficult to work with, but also when you put it down, it stays where you put it. Where if you don't tie regular PEX down, it has a slinky effect, and sometimes will cause problems if you don't secure it properly. PEX aluminum, where the regular PEX pipe followed a copper tube size diameters on the outside, PEX aluminum has different outside diameters, which means that you can't use the regular fittings. You have to use fittings specifically for PEX aluminum. And it also has a 200-degree temperature rating on it. The next type of pipe, and this is something fairly new to the U.S. market, we've seen it come through a little over 5 years ago. It's called PERT, P-E-R-T, and that's polyethylene raised temperature. It's a proprietary Dow compound, Dow X2344. They've been using it in Europe for over 30 years, and I've been told that the European market is really about half PEX, half PERT. PERT, being polyethylene, is not cross-linked, which means, of course, in manufacturing, they can run the pipe a lot faster. So it's less expensive to produce, which gives us a lower cost per foot of pipe also. One thing that you do have to note also is that 180 degrees is the maximum water temperature for PERT pipe. So you need to be aware of the temperature limits of PERT. PERT sometimes is called 5-layer pipe. We have an inner layer of polyethylene. Then we have an adhesive layer. Then we have the EVOH oxygen barrier, another adhesive layer, and then an outer layer of PERT. And that's referred to as 5-layer pipe also. The PERT pipe does follow the copper tube size outside diameter, so we can use the same fittings that we use with PEX pipe. PERT pipe is a little more flexible than PEX, so you can make tighter bend radiuses. with it, and comes in most of the same sizes as the other pipes do, 3/8 to 1 inch. The last type of pipe that we're going to talk about is Watts calls it Onyx pipe. Watts Radiant calls it Onyx. Onyx is a EPDM, more or less a hose. It has a EPDM basically cross-linked inside the pipe. It also has an aluminum layer as an oxygen barrier. And that aluminum layer is not as thick as the aluminum in the PEX aluminum, so it gives us flexibility. The aluminum is only there as an oxygen barrier. There is a spiral reinforced aramid fibers to give us a little more strength to the pipe, and then there's also an outer layer over top of the pipe. There we go. There's a picture of the EPDM, and you can see the braided fiber reinforcing is kind of in a cross-link pattern, which gives the pipe flexibility. Onyx pipe, you can pretty much tie it in a knot if you want. It's very flexible. It works well if you're doing, say, snow melting and stairs. If you're doing joist heating and you need to be able to pull the pipe through the joist spaces, it's very flexible. The other advantage is if you're doing a large area, a big warehouse or something, and you don't have a pump to pump the concrete in, you can actually back trucks over the Onyx, and it will not crush the pipe. The pipe will flatten out, but as soon as the weight comes off it, it pops back into its original shape, where you can't do that with some of the other pipe. The Onyx pipe doesn't, again, follow the copper tube size, so we have to use specific fittings designed specifically for the Onyx pipe. It also has 180-degree maximum temperature, so you need to be aware of that also. The bend radiuses are much tighter than the other pipe, even though some of the bend radiuses here 4-inch for half-inch pipe, you can bend it actually a lot tighter than that. The pipe may oval out on you or something, but it will still carry the same amount of water. Manifolds come in a variety of materials. You can see the stainless steel and the copper manifolds here. You can also get them in bronze or brass, and there are some polymer manifolds out there also. The manifolds basically serve as a connection point for all the loops in a system. When we put down radiant floor, we put it down in various loops to serve different areas and also to limit the length of each particular tube. Some of the accessories that you can get on a manifold would include the zonability of it. You can get shut-off valves on each individual loop. You can get balance valves on each individual loop. You can get flow meters on the loops, thermometers on the supply and return side, shut-offs on the supply and return side, air vents to vent the air out of the system, and also purge valves so that you can drain the water from an individual loop, or on installation, if you're trying to get all the air out of the system, you can power purge each individual loop, and the drain valve comes in to play when you're doing that. So you can get lots of different options and accessories on the manifolds, or you can go as simple as a piece of copper with stub outs on it and go from there. You can also get zone actuators that fit on top of the balance valves on different manifolds, and those could be wired to a thermostat so that you could actually put a thermostat and a zone control on each individual loop. So if you had a house where you have a bathroom on one zone, a bedroom on another zone, living room on a zone, and a kitchen on a zone, you could do 4 different areas with one manifold by attaching zone actuators to a manifold. A manifold installation, one thing we always want to be aware of is that you want to try to keep the manifold about 16 inches off of the finished floor. So when you install it, you want to raise it up above the floor level. The big reason for that is one, we have to sleeve the tubing as it enters and exits the slab, so you're going to have a little bit of the sleeve sticking up. And then you have to have some room to be able to attach the tubing to each individual loop on the manifold. And when you've only got a short piece of tubing to work with, sometimes it can be difficult to attach it to the manifold if it's too close to the floor. So leave at least 16 inches between the finished floor and the bottom of the manifold. There's just a picture of a mock-up of a manifold system. You can see the sleeves coming where they would come out of the floor, and then the short attachment distance between the sleeves and the bottom of the manifold. And that is mounted 16 inches from what would be the finished floor. So you can see there's a short distance there. So make sure you get it far enough up off the floor so that you can get the tubing connected. Heat transfer plates. A lot of times when we quote these jobs and we add heat transfer plates, they can be kind of pricey depending on which kind of heat transfer plate you're going to be using. And we have people, well, I want to do it without the plates. The plates are exactly what they say. They transfer heat. They make the system more efficient. And the added cost of a heat transfer plate usually pays off in both energy savings and creature comfort. You get better heat from a heat transfer plate than if you just attach the tubing by itself. And the reason that is because we have more surface of the tubing touching the heat transfer plate than if we just attached it to the floor. So the more surface area of the pipe we have touching, the heat transfer area grows with that. And if you've got a metal plate, aluminum or steel or whatever the material is, there's even graphite plates now. That heat is transferred along the surface of the plate so that we get a lot more even distribution of the heat. This is just a little thermal image. The top image is a system with heat transfer plates, and the bottom is just a staple up without plates. And you can see how much more floor area we cover when we use the plates than if we don't. So if you get someone who's not comfortable with the cost of the plates, you can explain to them that it's going to be more efficient, more comfortable in the long run, and over time they'll pay for themselves. A lot of people have, a lot of the manufacturers have floor panel systems of one kind or another, and this is basically a wood or other material that already has grooves machined into it to snap the tubing in, and you just lay it over the floor, screw it to the floor, and walk your tubing into the grooves in whatever pattern that you need it to be. Usually this is going to add about 5/8 of an inch above your floor surface, and then you would need to put a piece of underlayment on top of it if you're going to do something other than a tile. So if you're going to do a hardwood floor, a laminate, or a carpet, you would need to put a subfloor over top of this type of floor also. So you're going to be adding another 1/4 of an inch. So you have to make sure that you've got room for it. If you're doing a remodel with this, you're going to have to trim all of your door jambs and move your baseboard up. So there could be quite a bit of work involved in just getting the house ready after you've installed the floor panels. These particular panels come in 2x2 pieces, and you just lay them down and connect them end to end, and very easy to use. It's a medium density fiber board. You can cut it with a table saw or a circular saw. There's also a utility panel that you can use for odd configurations and make things go smoother for you. Pre-assembled panels. If you're working with a contractor who's not comfortable doing the piping, if you're working in a facility that wants everything to be enclosed, wants everything wired and piped so that you can get in and out of a job quickly. You don't have to do all the piping on site. Pre-assembled panels can be purchased in any different configuration. They can come piped, wired. You can put actuators on a manifold, have everything wired and ready to go. Sometimes they make the jobs a lot neater and a lot quicker to install. The installation methods would be the next part that we would want to cover. Different installation methods for different applications, and they don't all follow the same pattern. Sometimes the installation method is something that gets changed from job to job depending on what the end user wants out of their radiant system. The most common and the most cost-effective is concrete slab on grade, where we simply put down insulation and then attach our tubing either to a piece of wire mesh or staple it directly to the foam, and then pour the concrete floor right over top of the tubing. We see this very common. You do basements, garages this way, pole barns, shops, all kinds of different installations use concrete on slab. One thing that you have to remember is that if they're going to saw cut the floor, make sure that your tubing is at the bottom of the slab, and make sure the guys that are doing the saw cuts know that there's tubing under there. PEX tubing floats, so you want to make sure you secure it to the floor properly. We usually tie it about every 2 to 3 feet and make sure the tubing stays on the floor. That way we don't have to worry about somebody cutting a piece of tubing while they're saw cutting. Again, this is the most common and probably one of the most cost-effective ways to do radiant floor. This is just a cutaway of a concrete slab on grade. You can see the insulation under the floor and also along the perimeter. Perimeter insulation is important because that heat will migrate through your outside wall, and you're going to lose a lot of heat to whatever's on the other side of the wall. If it's just the outside of the building, you're going to have a little radiator going out there. If it's under the surface, you could have grass and flowers growing next to your building all winter long. So you want to make sure that you get the perimeter insulation in there also. A lot of times they'll put 6x6 wire mesh down, and you'll use nylon ties to attach it to the mesh. 6x6 mesh is really nice. If you're doing 12-inch centers, you just put a piece of tube on every other line of the mesh. You can also staple it with plastic staples and just staple it directly to the foam insulation. I usually recommend that you insulate under the entire slab unless it's a massive amount and it's going to be cost prohibitive to insulate under the whole thing. For most applications, you always want insulation under the slab. This is I missed a slide? No. This is an installation where we would be pouring over a wood floor, a wood subfloor, and we would attach the tubing directly to the subfloor, usually staple it or use a nailer to fasten it to the floor, and then they would come in with a gypsum overpour, the same type of product you use to level floors in large buildings. It's a slurry, so you just kind of they bring it in with a hose and just pour it on the floor. It's self-leveling, and then you can put your finished floor over top of the gypsum. One thing you have to remember when you're doing this kind of overpour is you want to have at least 3/4 of an inch of overpour above the top of the tubing. So you've got, if you're using 1/2-inch tubing, the OD of the tubing is 5/8 plus 3/4 overpour. You're looking at a minimum of 1 1/4 inch overpour if you're doing a gypsum slab, and then you would insulate underneath of that slab. Insulation, a rule of thumb is you figure out how much R value you've got from the tubing and above it, and then you insulate 4 times that underneath. So if you're putting a hardwood floor down and that floor has an R value of 1, you would put an R value of 4 underneath the floor. This is an example of a sleeper system using plates, and this is a less expensive way than gypcrete. A lot of times the gypsum overpour, it's hard to find someone to come in and do small areas. So you can use a sleeper system with the aluminum plates, and basically what you do is you take some either 5/8 or 3/4 plywood and you rip it to 6 or 8 inch width and leave enough room to put the tubing and the plate between each sleeper, and run that down over the floor, and then you would put a subfloor over top of that and your finished floor on top of that. And again, you would insulate between the floor joists underneath. This is a lot easier to do if you don't have availability to the gypsum overpours. And then also, you can put the tubing down just between the sleepers without the aluminum plates. This is a lot less expensive, but again, you're probably going to see higher water temperatures in your tube, and it's not going to be quite as efficient as if you used the plates. But this would just be a sleeper system where you would cut the wood and just lay the tubing between the gaps between the wood. This is a cutaway of that sleeper system without the plates. And then a lot of times when people are remodeling, they can get to the floor from the basement and they want to do their first floor in radiant. If you can get to the floor joist, you can put tubing between the floor joists. And that tubing usually goes on 8-inch centers with a 16-inch center floor joist. And we always recommend using plates, especially if you're going into an older house where you may have extremely thick subfloors. Sometimes you'll actually have 2 subfloors. If you've got 2 layers of 3/4-inch subfloor and then you're putting a finished floor on top of that, we're going to have a pretty high R value on top. So we want to get as much heat transfer from the tube as we can, and we do that by using the plates underneath of the floor. And then, of course, we insulate under that. This is what we see most common in remodel situations, is rather than put something on top of the floor, they go under the floor. That way they don't have to trim all the woodwork above. You would use 2 plates under the floor, one for each tube that goes under each joist space, and with the 8-inch centers, you have 2 tubes under each joist space. Typically, you don't want to go 1 tube under each joist space because that's going to put you on 16-inch centers. In a residential application, 16-inch centers, you're probably going to get some stripping. You'll be able to, if it's a tile or a linoleum floor, you'll be able to feel the cool spots between the tube if you go too wide on the centers. So we try to keep it 12-inch or less on a residential application because the floor temperature is going to be noticeable if we have some streaking going on. So for underfloor, we try to go on 8-inch centers between the floor joists. There is a method where you just staple the tubing up under the floor, and then you leave an air space between the tubing and the insulation, and that air space basically acts as a heat transfer medium. This is not a very efficient way to heat the space. It's more of a floor warming technique, and you can get pretty high water temperatures when you're doing this, depending on what the R value of the finished floor is above. We don't usually recommend this. We do use it quite often when someone just wants floor warming. As a heat source for the whole house, it's not as energy efficient as some of the other methods we have. And really all you do is you go through and you staple the tubing up between the floor joists directly to the subfloor. Sometimes they'll leave a gap, use a click type fitting where you screw the fitting up to the floor and then snap the tubing in, and you get a little surface, you get a little distance between the surface of the floor and the actual tube. And it turns more into a radiated than actual radiant type floor. And you can see they're recommending a minimum of a 2-inch air gap between the subfloor and the insulation. The next part we get into is design, and this is where things sometimes get kind of difficult sometimes when you get a drawing in that looks something like this, and the people who want the radiant design don't really give you much information sometimes to work on, and we kind of go by some rules of thumb in order to try to get these projects accomplished. The more information we can get, the more detail we can give you as far as heat loads and piping lengths, how much tube we can put in a floor, and what our energy efficiency is going to be. So we try to get as much information as we can. A couple of those guidelines we use, maximum floor temperature is 85 degrees. No matter what kind of a floor surface you have, you never want anything more than 85 degrees. The big reason is because it becomes uncomfortable to stand on. It's too hot to walk on. The other reason is probably a more financial reason would be is you can crack or warp the floor coverings, and sometimes the adhesives can break down. If you're doing a thin set and it gets above 85 degrees, a thin set for tile, sometimes that thin set will start to break down and then your tile will come up. And that's not a situation anybody wants. So we try to keep that floor temperature no more than 85 degrees. Certain hardwoods may call for an 80 or 82 degree maximum temperature, so you'll want to check with your flooring people before you design the job to make sure that you can achieve that floor temperature. We usually tell people that the maximum output we can get is 40 BTUs per square foot. And you can see in the chart there various set points of room set point, 72 degrees with an 84.5 degree floor temperature, we're down to 25 BTUs per square foot. Where if we lower that temperature to 65 degree room set point, we have an 85 degree floor temperature and we can give you 40 BTUs per square foot. But it's going to depend on what the set temperature of the room is. Typically with radiant floor, your set temperature is going to be a little lower. 68 degrees is pretty common for radiant floor because it's so much more comfortable in the room that you don't always have to turn the thermostat up to be comfortable. When we're designing the systems, we want to design somewhere between a 10 and a 20 degree temperature drop through the tubing. I typically design at 20 degrees. It makes things a lot more efficient from my point of view. You get the most heat transfer at 20 degrees, and so that's where I like to design. I do see jobs come out at 10 and 15 degrees, which is fine. You just need to move the water a little quicker, size your pumps a little different, and you're not going to get as much heat transfer through the tube when you go to the lower temperature drops. Information. Information is key. The more information we can get on the job, the easier it is for us to design that job and get it correct for the application. So we always want to know who we're designing the house for, if it's a contractor, wholesaler, engineer, architect. Tell us who you are. Tell us how we can get a hold of you. Give us a project name. We get a lot of projects in when we're doing designs, and you know, we without a project name, sometimes it's hard to distinguish between different projects. I mean, you can only have so many 36 by 48 pole barn project names until you start to get them confused. City and state is important because we need to know what the outdoor design temperature is. And when we're designing, we do follow the ASHRAE standards for design, so that design temperature is important for our designs. And then we would need to know the application. Is it going to be a slab on grade? Is it going to be a thin slab, staple up? Are we doing subfloor? Are we doing above floor? Is it going to be, what's your joist spacing? All those things come into play when you're designing one of these jobs. So information, again, information is key. And the more of it we get, the quicker you'll get a quote back, the quicker it is to design. Some of the construction details, of course, would be room names, zone. If you're going to have more than one zone in the area, if you're going to group all the bedrooms together, they might be zone 1, the kitchen might be zone 2, the family room might be zone 3. Give us that information so that we can zone it the way that the end user wants it done. Some of the information we hardly ever get would be floor covering. We don't know if it's going to be a tile floor, a wood floor, carpet. You can put carpet on radiant floor. You just have to design that into the job so that we know what kind of R value we're going to have above the heated surface. Ceiling height probably isn't real critical, but it's always good to know. With radiant floor, we're more interested in the first 6 feet of the room, from the floor up to about 6 feet. We want to keep that space warm. If you've got an 8, 10, 12-foot ceiling, we really don't care what it is at 8 foot up. So, you know, the ceiling height is good information to have, but it's not always, doesn't always make that much difference in the calculations. A drawing, if you can give us a drawing, that always helps us a lot in the design of a system. The next thing is we've talked about loops, how we have multiple loops in an application. For different size tubing, we have different recommended lengths. And the reason we use those recommended lengths is because as we add tubing to a loop, it increases the pressure drop through that particular loop. And as everybody knows, pressure drop makes the size of the pump. The more pressure drop, the bigger the pump. The bigger the pump, the more money we have to pay for that pump. So we try to keep the pressure drop down to a minimum. So the loop lengths, the recommended loop lengths, keep that pressure drop in a manageable range. It also makes sure that we get even heating through the floor, because if we're on a 20-degree temperature drop and we've got a length of tubing that's longer than the recommended length, when it gets to the end of that tubing, the water temperature is going to be 20 degrees difference or more. When we get into a 30 or 40 degree temperature drop, the end of the tube doesn't really generate much heat, so we're going to have cool spots on the floor. That's usually not good for comfort. There are also some recommended gallon per minute through tubing at those lengths, and at a 20-degree temperature drop, 1 GPM is going to give you 10,000 BTU. So if we go 300 foot with half-inch tubing, 1 gallon per minute, that loop would give you 10,000 BTU theoretically. On-center spacing. Typically, if we're doing residential, the easiest thing that we can do is give you a 12-inch spacing. The nice thing about a 12-inch center is that it's far enough apart to keep your tubing costs down, and it's also not too far apart that it gives you streaking in the floor. 12-inch centers is a good center to use for comfort. The whole floor feels warm, and it's easy to calculate. You use 1 foot of pipe for every square foot of floor surface. So if you've got 250 square foot of area, you would need 250 feet of pipe, plus the leaders from the tube up to the manifold. You always have to add in another 5 feet, 6 feet for the leader length. So you always have to remember to add that in. If you're doing different tube centers, you have to realize it's going to take more pipe. If you're doing 6-inch tube spacing, it's going to take twice as much pipe as if you were doing a 12-inch tube spacing. If you're doing a warehouse and all you're trying to do is space heating and you stretch it out to 24-inch centers, you're going to use half as much tubing as if you were on 12-inch centers. So the tube spacing comes into play as far as comfort goes and also as far as cost goes for tubing. Piping layout, the big thing to remember with the piping layout is always get the hottest water to the outside wall. The outside wall is where we have our highest heat loss, so we want to get our hottest water out to that wall as quickly as possible. So we would run the tubing out to the wall and then serpentine it back to the exit point of the room. That would be for a single heat loss wall. If we have more than one outside wall, we can do a double serpentine where we bring the hot water against the two walls and then work our way back to the exit point of the room. Tubing layouts can get complicated if you've got a lot of outside walls, but for the biggest thing is if you get the warmest water against the outside wall, follow your center-to-center distance back to the exit point, it's pretty hard to mess it up. And radiant floor is pretty forgiving, so if you make a mistake on the tubing layout, it will usually still heat. It's hard to make a system not work, so very forgiving. If you're doing floor warming, say in a bathroom with a tile floor where you're just interested in floor warming, sometimes you'll use a counterflow spiral that basically spreads the heat out a little more evenly across the floor, and it gives you more heat at the center of the room where most people will be standing, and if we're doing floor warming, that's important. You want the warm floors where the people are going to be walking. And if you were born in the 60s, this is one that you can stare at for a while. I would never, ever attempt to put a floor down like this, but it's really cool. It's in color, and it's got all the multicolors, and if you stare at it long enough, it looks like it's moving. Back to our design. We saw the drawing that was sent in the first slide for the design, and this is what it would look like with the tubing laid out. Basically, we've got several different zones, and we've actually brought this back to two manifolds. Kind of hard to see the second manifold, but there are two manifolds there. So we can zone with the manifolds, or we can zone by manifold, which means that we can use one manifold to take care of a whole zone, or we can add actuators and zone by loop also. Then we get designs that come in like this. Here's a request for a radiant slab. They're looking for a material list and a quote. Here's what I know. It's a 20 by 25 wood shop, 10-foot ceiling, R38, which is the insulation above the ceiling. We got a 72 by 68 double door, a 36 by 68, basically a man door. We've got two windows, R19 walls. They want to be able to maintain a 55-degree temperature. Please let me know if you need any other info. Usually when you call them back, what you see is what they know. So you just kind of make some educated guesses and try to come up with a design. And some of those design would look something like this, where you just basically draw the walls, you drop in some doors and windows, put a manifold on it, and put a couple loops in it, and usually that's really what they're looking for. Typically something like this, you're going to be looking somewhere in the neighborhood of 20, 25 BTUs per square foot, and we can calculate the boiler load from that. And also, by knowing what our load is, we can also calculate the pump size too. It's always nice if you can get an architectural or an engineered drawing. If you get those in a PDF, usually you can import that into a LoopCAD system or an AutoCAD system and trace out the walls, trace out the zones, find out where they want their manifolds in the system. Usually we try to put a manifold in an inconspicuous location, behind a door, in a closet, in a utility room, somewhere out of the way where you won't be looking at an access panel. Typically they put the manifolds between the walls and put an access panel over it so that you can get in and make adjustments and any maintenance that you need to do. So a drawing like this is always great to see come in. Makes life a lot easier. From a system standpoint, with radiant floor, we can get as complicated as you want. You can put in 2 boilers. We can have baseboard, radiant heat, snow melt, swimming pool, and indirect water heater. All that we can do with hot water heating. By varying the temperatures to each particular system, we can take care of just about any application you want. We can, heat sources are pretty flexible. Anything that will give you typically hot water up to about 130 degrees, we can usually work it into a radiant floor system. And there again, we can make them as complicated as you want, or we can make them as simple as you want. We see a lot of these type of jobs come in where they want to use just a standard tank-type water heater on a small garage or an application like that. We dedicate that water heater to the floor heating system only. We put in our boiler accessories, expansion tank, air separator, the fill valves, all that kind of stuff, and we add a pump, run that pipe to the manifolds and out into the floor. And this is a very simple system and can be very efficient also. If we get a condensing boiler in a system, condensing boilers condense best with cool return water temperatures. That condensing boiler is capable of, say, 180-degree outlet water temperature from the boiler. And a lot of times, if you're doing a concrete slab, we can see water temperatures entering the slab anywhere from 90 to 110 degrees, which means with a condensing boiler, we can set that boiler to generate 110-degree water. It'll come back at 90 degrees, and the boiler will condense at 92–93% in that kind of a situation. So condensing boilers and radiant floor complement each other very well. You can also use a conventional boiler. If you're doing an add-on or you want to use an 80% boiler, the end user doesn't want to upgrade to a condensing boiler, we can use a conventional boiler. There are some precautions that we have to take. Because radiant floor is going to be running at such a low water temperature, if we're using a conventional boiler, our return water temperature is usually limited to somewhere around 130, 140 degrees to keep that unit from condensing. We're going to want to protect it either with primary, secondary piping, a hydraulic separator, a mixing valve to mix the temperature back in, so that we get that, so that we don't condense that boiler. What you're looking for in the end is an accurate heat loss, so that we can size our heat source accurately, make sure we get enough heat to the surface of the building without oversizing the boiler, and all the information is contained in what we call a heat loss summary that we send out with our designs, and it gives you all the rooms, what the square foot is, and gives you the heat loss for all the different components, and it gives us a total design load for the system. That design load is an output of your appliance. So if you've got an 80% heating unit, you may need to upsize it a little more because you still have to have the output, where if you're working with a high efficiency unit where you're 95%, you still have the same output, but your input's going to be less because of the increased efficiency. So you always want to size these on boiler output. The next part of the system that we would see would be the system summary. This is going to tell you the number of circuits in each particular space. It's going to give you what zone it's on. It's going to tell you the tube spacing, the total length of pipe in that area. It's going to give you the R value of the floor covering that it was designed for. It will give you a heat load for each individual space, and it also gives us our pump size. It will give us the feet of head, the head loss, and the flow rate so that we can size our pump. It also gives you the total gallons of water in the system so that we know how much water's in the system. We can size our expansion tank from that. This is really nice. The particular program we use, LoopCAD, gives us what we call a coil cut schedule. Usually if we're doing a house, each room is going to be different square footage. So we're going to have a lot of different loop lengths. And what the coil cut schedule does is it tries to minimize the loss of tubing. If you've got a 300-foot roll of tubing and you only need 250 feet, you're going to have 50 foot of unused tubing, and the coil cut schedule takes all those different tubing lengths into account and combines them to get you the least waste out of each coil. We try to keep it down in the 4 or 5%. Sometimes you can't avoid it. You might get 10 or 11% what we call waste tubing that can't be incorporated into the job. But the coil cut schedule helps a great deal in minimizing the unused tubing. We also have our radiant panel schedule. This basically tells you what type of floor we designed. Gives you, if we're doing an overpour, would tell you the thickness of the overpour. Would tell you what the insulation under the floor was calculated at, and gives you a little diagram of how the systems will be installed. And then last but not least, we'll give you a material list with a quotation so that you can calculate what the cost of the job is going to be for the radiant material. The program is customizable so that we can put in other components. We could actually put in a particular boiler or a particular pump that the end user wants, the wholesaler, contractor, whoever wants to use a specific brand. We can add that into the quotation and give them a complete job quotation. That's pretty much the end of my part of the presentation. We can take any questions you have now.
Yeah, we'll start with the questions that came in. First question is, Phil, how much insulation should be used under the slab?
Typically what I tell people is you put as much insulation under the slab as you can afford. The more insulation, the better you'll be. Under a concrete slab, we typically see 1 inch of foam board, styrofoam, polystyrene board underneath, which would give you an R value of 5. 2 inch is also common, which will give you an R value of 10. Underfloor, if you're putting up fiberglass insulation between the floor joists, usually at least 4 inch. A lot of times we'll go 6 or 9 inch insulation under the floor joist. But my quick answer is put all the insulation you can afford.
Okay. Any more questions? Okay. Well, thank you, Phil, and thank you, everybody, for attending today's class. You should see an SBCU certificate soon in your email. Tune in for our next class covering backflow prevention. It'll be on November 5th, hosted by Brett Mullins. We also might have a bonus class coming in December covering wastewater treatment systems. Please email me if you would be interested in attending this class. It might just be a private class to help for those interested. Thanks again, everybody, and enjoy your day.